Hello everyone, welcome back to our engineering mechanics dynamics. Today we're going to solve the problem, a cylindrical components problem. This will be our example 1. It is against the chapter 12.8 that we covered. And then in this problem we're going to do twirling, meaning something is rotating and it has an outward velocity and acceleration. So we're going to determine those. So let's see our problem. Um, so our learning objectives is solve a curvilinear motion cylindrical component problem. In example 1, we'll be applying polar coordinate system to determine the polar components, magnitude, and direction of velocity and acceleration. And like we said, we're gonna study twirling problem, meaning something is rotating, and then we will have a pipe rotating circular motion, and the water particle will move outward towards the pipe. So we'll see what is we'll determine the velocity and acceleration of that water particle. So let's see the problem. The problem says a man is twirling a hose on r theta plane such that theta equals to 0.3 t to the power cube, where t is time here, and then theta is in radian. At the same time, a water particle is moving outward along the hose pipe, meaning the water particle is inside the pipe. Since the pipe is rotating, the water is tending to move outward. The particle position is defined by r equals to 200 t squared. So with time, the position of the particle r follows this equation in millimeter. Now at t equals to 1 second, the problem wants us to determine the polar components, magnitude, and direction of the velocity and acceleration of the particle. So imagine that a particle is inside a pipe, water particle, and then it's moving inside the pipe, and we have to measure the velocity and acceleration of the pipe. So what are the givens? What are the knowns? Let's see what are the knowns. R equals 200 t squared, that is given, and theta equals to 0.3 t to the power cube radian. So when the question asks at t equals to 1 second, so we're going to find what is the position at t equals to 1 second. If we plug that into the equation, we found t squared equals to 1, so r equals to 200. And theta equals to 0.3 at t equals to 1 second. 0.3 radian at t equals to 1 second, which should be 17.19 degree. So we converted from radian to degree. We know pi 180 degree equals to pi radian, so you can convert it from there. So these are the knowns. So what are the unknowns? So the problem asks at t equals to 1 second, find the components, meaning the vector components, cylindrical components of the velocity, its magnitude and direction, the angle. Same thing for the acceleration, its components, its magnitude, and its angle or direction. So let's draw a diagram. So the diagram you see is for example, if the man is twirling, same way as the cowboys throw their lasso. So if you're a bird looking from top, so you'll see the pipe, and the particle, the red dot is the particle inside the pipe moving from the origin O, and the pipe is rotating in this direction. So it will be rotating in this direction. So current position is theta, and which is 17.19 degree, and then this is our particle. It is moving along the pipe. So let's solve the problem. So we know the formula, velocity equals to r dot in unit vector in r direction plus r theta dot unit vector in theta direction. Same, we have the equation for acceleration. Now we see in those both equations, because we need acceleration and velocity, we need r dot, which is the first derivative, r double dot, which is the second derivative of r, and theta again, theta dot, first derivative of theta, and same for theta double dot is the second derivative of theta. So let's find those first. So all the derivatives at t equals to 1 second, we'll determine those because we're looking for those values at t equals to 1 second. So r dot, the first derivative, is if we take the derivative of the given equation, r equals to 200 t square millimeter, we'll get 400 t, and then when t equals to 1, we get 400. Similarly, we're going to do for double dot, which is 400, and similarly theta dot, the derivation of theta equation given. So if we take derivative of theta equals to 0.3 multiplied by t to the power cube, if we take derivative of that, we'll get theta 1 and theta double dot, all these values. So from there, if we plug these values back to the original equation that we have up here, so we'll get v is 400 in radius ur, and 180 in unit vector theta direction. And then how to find the magnitude? So we know x component whole square and y component whole square, that gives us 438.64 meter per second. So how do we find the direction? This is kind of tricky. So we know that if we know the x and y component, if we take tangent inverse, so which is our this part, so y component, which is 180, and then x component, which is 400, so that will give us the angle, which is which will give us the angle of the velocity of this particle. So this is the velocity v, right? And then it will give us the angle, this angle. So but we need to know the angle from here, so we're summing up the theta, so theta and lambda. So this angle is delta and this is theta, so this is theta, so we're summing this angle plus this angle, then that's how we get the angle orientation of velocity 41.42. So let's find the next part, the acceleration. Again, we're going to use the same value, the derivative we found, so we're going to just plug back to the acceleration equation. If we do that, the value of r double dot, r theta dot, so if we do that, we found this equation, and just simple math, we found the x and y component of acceleration, and magnitude is the same way, and that gives us 1105 millimeter per second square. And angle, the same thing again. We have our equation, and since you see the x component of acceleration is 238 positive, so that's why our direction is positive here, and then y acceleration is 1080 in theta direction, positive. So we have our angle, so we'll get this angle. If we had 283 kind of negative, for example here, if we had negative 230, well, negative 238, so our direction of r would be this one, and then our a would be this one, and we would get the angle this one instead of the angle we're having right now. So that is the adjustment we need if we had negative, but now we had all positive, so we don't have to worry about it. So we have r in this direction and theta in this direction, so we get the phi as this is the angle, and we need the original, so this is theta, so the total angle is theta plus the phi, so we'll get 94.76, and this is our answer. So in next video we're gonna solve another problem. Till then, see you. Thank you.